Madam Esther, can you hear me?
Yes, I can hear you.
I thought you're not going to come back again now. You still came back.
I still came back. I knew you would come back first.
Okay, now. I was
Mm.
not doing that. I was just saying, okay, let me just allow them see if one or two persons will come back. Okay, now. So you are seeing that this man like teaching too much. Okay.
Not really.
Okay, let's look at this question now. 3Cl2 plus 2H2O, a reversible reaction, gives you 4HCl plus O2.
Sorry, come again. Sorry.
3Cl2,
Okay.
2H2O, your equation which is reversible, 4HCl plus O2. Enthalpy change is plus 115 kilojoules. Is that taken?
Yes.
Okay, the question that follows is this. Maybe just listening to the options now. In the above equilibrium reaction, a decrease in temperature will dash. A decrease in temperature will dash. A, favor the reverse reaction. B, favor the forward reaction. C, have no effect on equilibrium state. D, double the rate of the reverse reaction. Do you get the options?
Please, the question again.
In the above equilibrium reaction, a decrease in temperature will dash. A, favor the reverse reaction. Favor the reverse reaction. B,
Okay.
favors the forward reaction. C,
Okay.
have no effect on equilibrium state. Are you there?
Yes, I'm here.
Double the rate of reverse reaction. Double the rate of reverse reaction. So what do you think is the answer? At least I'll be talking and explaining things. So this is a jam question. It's not me that said it is jam. Are you ready?
Sorry, what is option B again?
Option B should be favor the forward reaction. That means they ask you that in a decrease in temperature. That means they're simply asking you, if you decrease the temperature, what happens to equilibrium position? A decrease in temperature. So how do you explain this to the students? Tell them, watch out for enthalpy change. That's the first thing to check. Now, enthalpy change is positive, meaning that the above reaction is what type of reaction?
It's endothermic.
Endothermic. Now go to the part where
Yes.
you put exothermic and endothermic. For endothermic, if you decrease temperature, what happens to equilibrium position?
So, okay, equilibrium position will shift to left.
So that's it. So a decrease in temperature will favor the reverse reaction, which is option A.
Okay.
So that's the answer. So these are the kind of applied questions that I was talking about. I wanted us to look at, that's why I came back. Otherwise, I would have just go completely, but it would not be nice if I don't touch this aspect. Okay, is that okay?
Okay, which one is the reverse reaction?
Reverse means backward.
Okay.
I have another one here, but let's just leave it. Right, Abi?
Okay.
Or I should ask you one more to see whether you understood the concept.
Please, if you can.
Okay. N2O4. I think we have written this equation somewhere before. N2O4
Yes.
give you 2NO2, that is reversible reaction. Are you there?
So yes.
Okay. And I said in the endothermic reaction above, more product formation will be favored by dash. More product formation will be favored by dash. First of all, do you understand the question?
More product formation will be favored by that.
Now, what they are simply asking you there is that which of the conditions will favor forward reaction?
Okay.
Okay. Now, the options are these. A decrease in pressure. A decrease in pressure. B, a decrease in volume. Are you with me?
Yes.
C, an increase in pressure. And D, a constant volume. Are you with me?
Yes.
Okay. So, any question? If the options are confusing, ask questions. I'm expecting questions from you now.
Yes, this one has to do with pressure.
Yeah, this one has to do with pressure. Now, that is the next thing which I want to talk about now, which is pressure. So, remember we said three things can affect it. We have explained temperature, we have explained concentration, right?
Yes.
Now, for pressure, always tell your students, pressure is applicable only when there is gaseous reactant or products. So for that equation now, they are all gaseous states. So you can write it there, attach it to the state of matter in that equation. Did you get that?
No, sorry.
That pressure is only applicable or pressure only affects equilibrium position if there are gaseous reactants or products.
Okay.
Did you get it now?
Okay.
Let me give you an example. Can you see the board?
Yes, I can see it.
Okay. I'm trying to see if I have. Okay, that's one example. We can also see right another one. 2CO2. Sorry, 2CO. 2CO gas plus O2 gas. Give me 2CO2 gas. Are you there?
Yes, I'm here.
Okay. In another case again, I'm trying to. Okay. There's one particular question where we wrote equilibrium constant that has to do with Fe. You see, have that equation there.
That's to do with
Fe, that is 3Fe plus 4H2O. You have that equation now?
Yes.
So that's another equation which I wanted us to write. Then for the state of matter, in that particular equation, are you there? You can repeat that equation now as number 3. The state of matter there is the Fe is solid.
Okay.
The H2O is gas. The Fe3O4 solid. While H2 is gas. Did you get it?
Solid, then the last one is gas, right?
Yes, solid and then gas. So now, what we want to explain is how does pressure affect these 3 equations? It could be more than this, but let's just use these 3. So let me start with the first one. This first equation, what is the state of matter?
Gas.
They are all gases. Now let's assume this is solid. I'm only assuming solid and maybe liquid. Which obviously is not possible, okay. But let's just assume it's something like this. You have gaseous state. Yeah.
No gaseous state. Yeah.
Okay. So if you have an equation like this, whereby none of the reactants or the product is gaseous, if you like, increase the pressure till Jesus comes, or decrease the pressure, equilibrium position remains the same.
If you have sorry, come again.
I come again. That means if there are, remember we said the first one was that if there a change in pressure is only applicable when the gaseous reactant or product, right?
Okay.
Now the opposite to that statement is this: that if there are no gaseous reactants or products, a change in pressure will not affect equilibrium position. So that's why I gave this example. I usually have this as solid liquid. Since there's no gas here at all, if you like, increase the pressure or decrease the pressure, equilibrium position will remain the way it is. That is Odeshi. It will not change. It will not move to the right, neither will it move to the left. Is that okay?
Yes.
Okay, so now let's return it back to the way it was before. This aspect, when I'm explaining, I know I will explain because it's very tricky. So I always start by drawing this diagram for students. It will help them. This diagram is from the gas laws. One, two, and maybe three. Did you see the diagram?
Yes.
Okay. So what does this diagram imply? What can you say about this diagram?
Okay, that as the pressure is, as it's going higher, the pressure is reducing while the volume is increasing.
Okay. As pressure reduces, volume increases, or whatever we want to put it, as the volume is reducing, pressure is increasing.
Okay.
So that simply means this, that once there's an increase in pressure, it favors the side with a smaller volume.
Favors is smaller volume.
Yes. Once there's an increase in pressure, it favors the smaller volume. And when there's a decrease in pressure, it favors the side with the higher volume. Do you get that statement?
Yes.
Okay. Now let's consider this equation that we have here. We have one here, invisible one. So I'll put here, maybe I can write here total volume. Total volume. This is 1 and this is 3. Why this is 2? So total volume here will give me 4. That is 1 plus 4. Why this one remains 2? That is 2 volumes. 2 volumes. Any question?
No question.
Okay. So why am I adding it? Is because they are all gases. So gas. And with this gas, solid gas, I would know what I will do when I get to that bridge.
Okay.
Now, I will say this, and I will establish this, and also from that diagram that we drew, if I increase the pressure, which side has a smaller volume? Is it my product or my reactant?
If you increase the volume.
Let me draw the diagram back again so I can help you as I'm explaining. Remember your diagram. Big volume, sorry, big pressure, small volume. Small pressure, big volume. Right?
Yes.
So if I increase the pressure of this reaction or of this system now, which is already in equilibrium, and increase in pressure means my P is big. It should favor which side?
To measure the volume, the view,
The small v,
the
right?
small volume.
Yeah, the
Yes.
small volume. And which side has the small volume? The forward reaction.
Action, yes.
So an increase in pressure will favor the forward reaction.
Okay.
You know the reason already, because of the volume is smaller on the product side. Do you understand?
Yes.
Okay. And it's the same thing for if you now decrease pressure, if you favor bigger volume, that means this side. So in case a student is asked now, list 3 factors that can increase the yield of ammonia. What are the 3 factors? Can you tell me now? Can you hear me?
Sorry. Yeah, can you hear you? You say what?
List 3 factors that can increase the yield of ammonia in the above equation. That is in this equation. List 3 factors that can increase the yield of ammonia. What are the 3 factors the student will write?
An increase in pressure.
Okay. 1, increase in pressure. 1. 2.
Decrease in volume.
No, volume has no business here. What are those 3 factors that affect equilibrium position? Pressure, temperature, and concentration.
Okay. Yeah.
And so those are those 3 things. Now, one of them is increase in pressure. Very correct. Number 1. Number 2, decrease in temperature.
Okay.
Because the reaction is exothermic. I'm only relating it back to those other 2 that we've done, so you find out how they are all interlinked together. Then the third one is increase in concentration of the reactant, which you can put in brackets N2 and H2.
Okay.
So let me explain the second one and we'll close. My voice is almost gone.
Mm-hmm.
So what was the second equation?
2CO.
2CO react with O2. I think I should have 2CO2, right?
Yes.
Gas.
Yes.
So if I increase pressure, equilibrium position will shift to where? Right or left? And increase in pressure.
To shift to right.
Shift to right. Let's see. This is 2 plus 1. That is 3 volumes. And this is 2 volumes. So once you increase pressure, it favors the side with a smaller volume.
Yes.
And the right has a smaller volume. So it will shift equilibrium position to the right, leading to more production of CO2. While a decrease in pressure will shift the equilibrium position to the left, favoring the backward reaction and leading to lesser production of CO2. Any question?
No, no question.
Okay, thank you very much. Message passed across. And the last equation is what? 3Fe, I think that's solid, plus 4H2O, which is gas, giving me Fe3O4. No, no, I think this should be solid, plus H2, gas. Right?
Okay.
This was the equation now. that I said you should write before.
Yes.
What is missing? Something is missing in this equation. It's not balanced. So what is the balanced state of that equation?
4H2.
Okay.
The last H.
Okay, the last H, 4.
Mhm.
Are you with me?
Yes, I'm with you.
Okay, so the question here now is that in the above equation, an increase in pressure will shift equilibrium position to where? Is it right or left?
We still shift it to right.
Why? Why right? Or you just did a guesswork?
Because of the smaller volume. Because of the smaller volume.
Okay. How do you arrive at the smaller volume, please? Help me out.
This one is solid and gas. So.
Now you have seen the error yourself too. I love that.
Yes.
So if you see now, this is solid gas, solid gas. It is only the gaseous part that we will consider, which is this and this. Are you with me? Now, if you check the gaseous part, which I circled, this is 4 volumes, and this is also 4 volumes. So since the number of volumes are equal, there will be no change in equilibrium position.
Okay.
So that's the part I want to draw your attention to. Once you have equal volumes, there is no change in equilibrium position. Either you increase it or you decrease it, equilibrium position remain the way it is.
Since they have equal volume.
So with this, we have come to the end of today's class. And I think I can now take a leave. Any question? Any you are not clear? Let me know. Are you okay?
Yes, I'm okay.
Okay. Now, maybe you can on your camera. Let me see the face now. Every time the face is not seen. I'm only hearing the voice behind the face. Okay.
No, I'm not on it this time around. Because this face is not feeling too fine. I'm just managing.
Yeah, managing the face. It's good like that.
I'm managing the body.
No,
Body is feeling sick.
no problem. You are healed in Jesus' name. So unveil the face behind the mask.
The face is on holiday now.
The face is on.
It's on holiday.
Oh, the face is on holiday. Okay.
Yes.
Okay. Our resource person too is also going on holiday then. Since the face is on holiday, let us also go on holiday. Thank you very much for your time. So I'm logging out now. Can you hear me? Can you hear me?
Hello?
Hello. I said I'm logging out now. Can you hear me?
Okay.
Okay. Since the face is on holiday, that you please to show me the face. Let me log out now. Thank you very much for your time.
Okay. All right. Thank you too.